All right, so the last topic we were discussing in class was the definitive integrals antiderivatives note sheet, right? I don't know if you have that with you. If you do, then awesome. We're gonna look over a couple of problems, all right? So I'm gonna share a camera with you so you can actually see what where I'm gonna be writing and all that stuff. So give me 1 second here. Looks like somebody else. Oh, Victor is actually joining the class. All right, cool. Hello, Victor.
Okay, Michael. Nice background.
All right. So let me see. I need to share with you. Hello, Victor. All right. Okay. So we were working on this last class. And these are the rules of integration for the definitive integral. So let me just review that a little bit. It's called a definite integral because there are boundaries of integration. So in this case, we're integrating from A to B. Remember that, Victor, lower your phone. Okay, lower it at least. All right, so look, it's called a definitive integral because we have limits of integration. These are the limits of integration, right? And up to right now, we have thought of the integral, the definitive integral as area, all right? So what does this say? This say that always when we have an integral from A to B, we are making this assumption. We're assuming that A is less than B, okay? So in other words, this lower limit is always smaller than the upper limit of integration, okay? So what happens if we switch that order? All we're doing then is basically taking a negative value of that integral. That's all that this is saying. If you reverse the order of integration, you get the what? The opposite answer, all right? The integral between A and A of a function is 0 because there is no area. Between A and A, all you have is what? 1 point, okay? So that's why the integral is 0. Now, the constant multiple. If you have a constant that is multiplying a function, then as with limits or as with derivatives, you can take that constant outside, right? So this constant now is multiplying the whole integral. That's what that rule is. Then here we have that if we're adding two functions and we're integrating over the same interval, then we can split this up into either a sum or a subtraction, all right? And then the additivity part is that, notice, we go from A to B. So let's say I have a function, right? This is A and this is B. Well, if C is in between A and B, then the area from A to B, this integral, right? Actually, I did this incorrectly. So this is A to C, and then A to B. So the area from A to C, this whole area, is just the sum of this area and the sum of that area, right? Mm-hmm. If the value B is in between A and C. Says place close attention to the limits of integration. This comes in handy when dealing with the total area or the order of the functions where we need to break the interval into two pieces. This is important. There are no rules for two functions when we are what? Being multiplied or divided. All right, we will have to come up with a way to integrate that. I'm gonna let you do this on your own. These exercises, I think they're very simple. And I wanna concentrate on this. I wanna concentrate on the average value of a function, okay? So the average value of a function is How do you take the average, for example, ages of all the students in the calculus class? You ask what the age is and you divide by how many students we have, right? Here will be similar. It says that in this example, it says that if we want to find the average temperature during a 24-hour period, so in this case, they're telling me that the interval goes from 0 to 24, right? So what would you do? Then what you're gonna do is that you're gonna take the temperature at different times. So basically, you're gonna find out what the temperature at time 1, what's the temperature at time 2, what's the temperature at time 3, until you get to the temperature at the last time that you're taking, right? And then if you wanna know the average of that temperature, then you're gonna add all this, and you're gonna divide by how many temperature did you take. In this case, we're going from 1 to n, so you will divide by what? N, right?
Mm-hmm.
So example 3 says, using this method, write an expression for the average temperature. Well, that's the expression. All the temperature values divided by how many you take, right? So here it says, if I'm going too fast, you let me know, all right? Here it says that the larger the number of measurements, the more accurately this will be. So it says, notice we can write this expression as a Riemann sum by first noticing the interval between the measurements will be this. So if we have an interval, I'm gonna write here, between 0 and 24, right? And I want to divide this evenly, then each piece, I'm gonna divide that by 24. So the length of the whole interval is 24, right? 24 minus 0, and I divide that by n. That is called the delta t, the interval. And from there, if I solve for n, I get this equation, right? So what they're saying here is the following, that if I replace this n by this expression, what am I gonna get? Well, I'll get f of t1 plus f of t2 plus f of t sub n over n, but n now is 24 over delta t. If we simplify this, it says substitute this value into the expression above and simplify. If we were to simplify this expression, then we're gonna get f of t1 plus f of t2, so on, f of t sub n, all that times 24 divided by, all that times delta t, because delta t, the denominator here, everything over 24, right? It says the last expression, meaning this expression, give us an approximate average temperature as n goes to infinity, meaning we are taking a lot of measurements or temperature readings. This Riemann sum becomes a definitive integral. So what do they mean? All right, so I can take this, right, and express this as a sum. I can say that this is the sum of what? F of t sub I from 1, because we started at 1, until n, right? Of what? What are we multiplying? Delta f of t times delta t. But also there is a 24 here, so I'm gonna write it like that. So what they're saying is that I can write this as a sum, and when I take the limit n going to infinity, this sum becomes what? A definitive integral, right? So a definitive integral is essentially the result of what? Of a limit. So that definitive integral is going to be, or how is that going to become? It's going to become the function f of t because since n goes to infinity, basically we're taking measurements at every moment of time, times dt, which stands in this case for the change of time, okay? What else is here that we don't have? The 24, and it's dividing, right? So I'm gonna actually write that there. Now, since it's a definite integral, I need what? Limits of integration. What is the interval that we are considering? A whole day, from 0 to what? To 24. So this will be the integral from 0 to 24. If you look at the properties, there is a constant inside here. That constant is 1 over 24. So I'm able to rewrite this as 1 over 24, the integral from 0 to 24 of f of t dt. And that's it. That is the integral. It says, is there any question up to this point? Anybody? Say no, Mr. Sanchez. Or yes, Mr. Sanchez, so I can know. All right.
You're good.
No,
Good.
Mr. Sanchez.
All right, we're good. All right, so example 6 says, do you think that there is any point during the day that the temperature reading on the thermometer is the exact value of the average temperature? I'm asking.
Wait, what?
Read example 6 and tell me, do you think that that's going to happen, yes or not?
Yes.
Yeah.
At some
Yes.
point, right? At some point, the average has to be equal to the temperature, right, of the function. So the answer to that is yes, obviously. At some point, it's going to happen. Okay? All right. So this is the basic definition. So the average value of a function, is defined this way. What are the conditions for that? The function has to be, if f is integrable. Let me see. Is there anything here that we didn't mention yet? All right, so we're good. If f is integrable on AB, and that means that this integral, we're able to find it. Okay, that's what it means right now. Being integrable means that we're able to find this value. So it says, if the function is integral on that interval, notice that the interval is closed, then the average value of the function is given by this. 1 over b minus a, so 1 over the length of the interval, this is the length of the interval, times the integral from a to b of f of x dx. Or the same thing as saying the integral over the length of the interval. Okay, that's the definition. So this basically summarizes what the average value of a function is. It's just the integral over what? The interval. It's just this integral divided by the interval. That's all there is. Okay. All right, so example 7 says the following. I'm going to try to do this example together. It says graph the function x squared on this interval. So x squared is going to be when x is 2, then it's going to be 4. When is 1 is 1. When is 3 is 9. Right? So basically, it's going to be this graph. Right? That's x squared. It says, all right, so that is my function on that interval. Set up a definite integral to find the average value of this. So how do I set that up? Well, the average value is just, what is the length of the interval? If it's from 0 to 3, the length is 3. So the integral or the average value will be 1 over 3, the integral from 0 to 3 of x squared dx. That will give me the average value. So set up this to find the average value on the, then use your calculator to evaluate that. So how are you gonna do this? Let me see if this comes up here nicely or not. Okay, so it's gonna be 1/3. You can go to,
I can't see the thing that you
okay,
wrote.
let me get closer. That's okay. Because this will be easier for me than toggle between one thing and the other, okay? Can you see that now? Better? Let me focus this thing.
Yeah, it's good.
All right, so we're gonna find 1 times the integral. We can do that through math. And we go to number 8. Actually, number 9. Function integration. So what are we integrating? From 0 to 3. What is the function? X squared. And here, all you put is the variable, and the variable in this case is x. So we need to find that value. So 1/3 integral from 0 to 3 of x squared dx. We haven't studied any methods to do this yet, so we're using the calculator, at least for now. We press enter, and the value is 3. So they're saying, okay, set up that and find that value on your calculator. Set up the definitive integral, find the average value, then use your calculator to evaluate that integral. Graph this value as a function. So what value are we graphing? 3, right? So this is the average value. 3, right? So it says graph this function on the grid. Does this function ever equal, does this function ever actually equal this value? Yes, where? At this point. The function equals the value where they intersect, right? Let me move this up a little bit, because otherwise it's kind of distorted for me. All right, so graph this value as a function on the grid. Does this function ever actually equal this value? If so, at what is the point? So if we're looking at this intersection, what are we looking at? X squared equals what? Because x squared is the function, correct?
Yeah.
And this value is what? 3. So we're looking at this equation, x squared equals 3. And we're on the positive side. So what x should be?
√3.
S squared root 3, right? So look at what it says. So this value here, down here, is a square root of 3. That's the value. That's the x value for which the average value of the function equals this. So it says, what do you suppose is the relationship between the area, between the x-axis and the curve, and the area of the rectangle? So let's find the area of this rectangle. What would be the area of this rectangle? How much is it?
3√3.
3 times 3. No, root of 3 is the x value. How high is this?
3.
3.
And what is the length?
3.
The length is also 3. So the area of the rectangle is 9. Right?
Oh, okay. I thought you were talking about this smaller rectangle.
Right. So no, the whole thing, this, right? Now, what is the area given by the integral from 0 to 3 of x squared dx? Well,
3.
let's find it on the calculator. All I need is to get rid of this 1/3. Right? Just the integral. How much is that integral?
9.
9. So the area of this rectangle and the area of the integral are
It's the
equal.
same.
Is the same. So what is this saying? It says, okay, what do you suppose the relationship between the area of the x-axis of the curve and the area of the rectangle is? Well, they are the same, right? They have the same area.
Mr. Sanchez,
Yes, sir.
are we going to learn how to calculate an integral without a calculator later?
Yes, we are. We are.
Okay.
We are going to do that. Okay. We're going
Got
to study techniques of integration. Okay.
Good.
We
Yeah,
just
got
use
it.
the
Thank you.
calculator to understand this concept. All right. So
My
look.
memories recall that's like currently it's still pretty simple, but once it started to involve like tangents and trigonometry and stuff, it's starting to get really annoying
It gets a little bit more complex. All right.
and terrifying.
You
Like
will-
you get like it's like I think it's like integrating I think it's integrating tangent or tangent x, and then you get something really complicated.
Yeah, it gets complex. All right, so look, it says the mean value theorem for integrals is basically saying this. If you are finding the area under the curve between x equals a, x equals b, and between, then there is one number c, look at that value in your graph, there is one number c between a and b whose function value, meaning this function value, f of c, whose function value you can use to form a rectangle that is the area or that equals the area under the curve. So basically, what we are saying is what? On the previous example, this is the value c between 0 and 3. And how much was f of a square root of 3? 3, right? In this particular example, f of the square root of 3 was equal to 3. But 3 was the average value of the function. Remember that we got this to be equal to 3? So the mean value theorem for integrals is telling me that I can find a value between a and b such that f of c is the average value of that function. Now, it doesn't tell me how to find this. It tells me that this one exists, okay? Now, we're running out of time already because this goes so fast. However, I'm not gonna do example 8, but I want to actually do the example 10. So if you don't have anything to do right now and you wanna stick around with me to look at this example 10, that would be great. If not, then we can do that in another occasion, or I can assign this as, in a way, independent study. All right. But I would like to at least read this problem because this is an all AP free response problem. Okay. So look, it says the following. Grass clippings are placed in a bin where they decompose for 0 to t, for t between 0 and 30. The amount of grass clippings remain in the bin modeled by that function, where A of t is measured in pounds and t is measured in days. So this is the amount of grass clippings. T is days from 0 to 30. So part A says, find the average rate of change. How do we find the average rate of change?
You take the first.
Take derivative.
Not the derivative. That would be
Like-
the instantaneous rate of change.
F of B minus F of
Average
A.
rate of change,
F of B minus F of A over B minus A.
exactly. Right? That's the average rate of change. So for us, in this Let's see. All right, Andrew, tell your mom you're still in class. But if you need to go, you can go. All right, so look. So for us, in this case, will be what? A of 30 minus A of 0 over 30, right? Because A is the function. So in this case, you can put that on the calculator. By the way, this is a calculator problem. And then you plug in 30 into this function, you plug in 0 into this function. If you do this part correctly with your calculator, you should get that this equals negative 0.197. Now, the units are key. This is pounds per day. So the average rate of change is telling me that the amount of clippings is reduced or decomposed at a rate of 0.197 pounds every day. Does it make sense? All right, so that's the average rate of change. And the reason why they put this question here is because they want to make sure that you don't confuse the average value of a function with the average rate of change, okay? So let's look at part B. So find the value of A prime of 15 using correct units, make an interpretation of the meaning of this problem. All right, so let's differentiate that, all right? So this is the function. So this is a constant. So A prime, this is a constant. So I keep it 6.687 times the derivative of this. Just to, for a refresher, what is the derivative with respect to x of A to the x? Does anybody remember?
You move x to the front and then you put 1 over a, I think, or 1 over x.
No, because it's not an exponential. I'm sorry, it's not a power. It's an exponential. So just to remember, this is ln of a times a to the x. Okay, that's the derivative of that. So that means that this should be ln of 0.931 times 0.931 to the t. So, and then you plug in 15 in there. If you plug in 15 and you have done this computation correctly, then you should get negative 0.164. Now, what would be the meaning of that? Somebody help me.
It will, the amount of like grass clipping would decrease by that much within the first 15.
So is the
I think it's like
so is the instantaneous rate of change? So on what?
on the 15th day,
On the 15th day, right?
they depose 0.164 pounds of grass
Per day, right? So,
yes.
so on the 15th hour, the grass clippings are decomposing at a rate of 0.64 pounds per day, right? That's what it means. Now let's look at this other question. Any questions from this?
No, sir.
All right, so let's look at C. It says, find the time. This is maybe the more complex problem. Well, these two. It says, find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass. Please mute your music. Find the time t over which the amount of grass clippings in the bin is equal to the average amount of grass. Let's look at this. There are two things. The amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin. So what are they asking for?
Yo, Victor, turn it off.
Just find T So the amount,
I think it's looking for the t where the instantaneous like change is equal to the average amount. So it's like the derivative equals to the integral where the t is.
no exactly, but look, the amount of grass, what is the amount of grass? A of t, where A of t is measured in pounds. So the amount of grass Kipling's is what? 8 of t, right? So they're saying in this problem, find the amount, the time t for which the amount of grass, A of t, in the bin is equal to the average amount of grass Kipling's in the bin. So the average will be 1 over 30, the integral from 0 to 30 of A of t dt. That's what they're asking us to find. To find the value of t for that. Okay? So, you find this value.
Yo, shut it off.
Please, somebody shut off, mute your music. All right, look. This value is the average value of the function. This is the amount of grass Kipling's. So we find this value and we set it equal to the original function. So basically, we get the following. What's the original function? 6.687.931 to the t. That's the original function. And we set that equal to this value. That value, if you place this in the calculator, that value is 2.752. This value, 2.752. So from there, you solve for t. And then t, you can use the calculator for that. All right, or you can divide by this and then take ln on both sides, either way. Then you find t. T should give you 12.414. Okay? So these are the type of problems that you may encounter if you were to take the AP test or on an assessment. Okay? Now, let's look at the last one. I'm running out of time because I have to do office hours in 10 minutes. I'm just at least gonna give you an idea how to do D, okay? It says, for t greater than 30, L of t, the linear approximation to 8 at t equals 30 is a better model for the amount of grass Kipling's remaining in the bin. Use L of t to predict the time at which there will be 0.5 pounds of grass clippings remaining. So I'm gonna give you the idea, okay? This is the idea for that particular problem. If you were to graph the function, that's a decreasing function. Why do I know it's a decreasing function? It's exponential and this is less than 1. So it has to be decreasing, okay? So the function is gonna do something like this. Somewhere here is 30. So what they're saying is that there is a line for values greater than 30, there is a line that is a linear approximation and is a better model for this. What line do you think is that gonna be? Or what type of line?
A straight line. Or what's it? Yeah. What's it? Tangent line.
Negatives. Wait, no.
A tangent line. Okay, a tangent line. So basically, they're asking you to do the following, okay? They're asking you to find an equation for that tangent line at 30, okay? And find out what value of t makes that line equal to 0.5, Read the problem, and then I'm going to leave you with that. And I want you to try this part on your own if you can. So I'm going to repeat the idea. There is a tangent line at t equals 30, okay? So we're going to estimate when that line, or we're looking for the time when that line equals to 0.5. That's what they're asking here. The amount of keepings, 0.5. So how do I do that? I need the equation of that line. But that line is tangent to this point. So what are you going to need?
The derivative.
You're going to need the
Derivative.
derivative to get the what? The slope where?
The slope.
Yeah, at that
At 30.
at t equals 30.
Right?
30. Yes.
And you need the point. You need the slope at 30, and you need the point 30 comma whatever the function is at 30. Does it make sense?
Yes.
So basically you need 30, a of 30. That's going to be the point that you need. And you need the derivative at 30 to be able to come up with the equation of that line. And once you have the equation of that line, you set that equal to what? 0.5.
0.5.
And that's your solution. Ladies and gentlemen, part D is your homework. Get it on a piece of paper, upload it at Canvas. I'll create the homework later on. I haven't created it just yet, but I will create it. Just this piece is your homework. Okay?
Or
All right. I'll be talking to you.
Wait, Mr. Sanchez. Mr.
Yes,
Sanchez.
Yes.
Is this worksheet on Canvas, like this file?
I can place it in Canvas in an announcement if you need to.
Put in like this. Put this like this exact file on Canvas so I can.
All right.
It'll be much better.
All right. I'll do that. Okay. Any other comment or question?
no, sir.
Okay, kids, stay strong, stay safe. All right. I really
Stay
need
sick.
class. Victor, where are you? Are you in China or you're here in Houston?
No, I'm in Houston. I'm
All
just
right.
not in the dorms.
All right. Okay.
I'm in my home.
All right. In your
My
home right now.
pillow.
All right.
and everything.
All right. Isha, take care. Daniel, take care.
Oh,
All right.
search internet for.
Nico, everybody, stay safe. All right.
Thank you, Mr.
Bye.
Sanchez.
You're welcome.
Bye.
Bye-bye.